Great, so now it's 1:10, we can start. Hi everyone, we have a new and exciting speaker today, CIOSEK. He comes from Microsoft Research, and he will be talking about imitation learning, a very exciting area within the space of reinforcement learning. So welcome, Kamil. Looking forward to listen to you.
Thanks a lot, and thanks for having me here. Before we begin, let me cover the logistics. So there's going to be 2 sessions, and each session is designed to be 50 minutes long. So the intended division in terms of time is I'm going to talk for 40 minutes, and then there's between 5 and 10 minutes for questions. We'll prioritize questions about imitation learning, since this is what the talk is about. But if you want to ask about reinforcement learning, or more specifically, the kind of reinforcement learning that we do at Microsoft, feel free to ask that as well. All right, so without further ado, let's get going. So let's say you want to play a computer game. You want to play Minecraft. Everybody loves Minecraft. And the thing is that, training an algorithm, training a bot to play Minecraft it's a pretty complicated affair. So there's this new technology known as reinforcement learning that allows us to train these bots. And just as a recap, in reinforcement learning, we have a feedback loop. So we have a policy. A policy executes actions. We have the environment, and the environment gives us states and rewards. So if you want to think about this game analogy, the policy is the bot we're training. So it is doing stuff in the game world. The actions is what the bot is doing. The environment is the Minecraft game. The state is the situation in the game. So it's where each character is, what's happening in a game. And the reward is what we want to achieve with reinforcement learning. All right. And in terms of formalization, so with these things, it's always good to have a clearly defined mathematical formalism. And the formalism we are going to be talking about today is known as the MDP. And specifically, we're going to talk about the average reward version of the MDP. So there's a slight difference here. In imitation learning work, this version is more popular. In more traditional RL, there's a discounted MDP, which is very similar but slightly different. So in an MDP, we have a set of states, we have a set of actions, we have transitions. So given I'm in a certain state and I'm taking an action, I have a certain probability of successor states that I can transition to, and I have a reward which comes from an interval. So it's between 0 and 1. And now when I have a policy, so given a policy, we can generate trajectories. Now, a policy is what the agent is doing. So formally speaking, a policy is a mapping from the state space to probability distributions over actions. And when I have the initial state, P0, and then I take an action using my policy, and then my environment transitions to another state, and then I take another action, and so on. That's how I generate trajectories. And because that process involves randomness, so my policy is allowed to be stochastic, and the transitions are also probability distributions. The trajectory tau is a random variable. So each time I roll out this feedback loop in a system, I will get different trajectories. Okay, so well, you might ask, sure, yes, fine, but what's the goal? What's happening? Like, what's the purpose of having these policies? So we kind of mentioned earlier that, using our Minecraft analogy, the goal of reinforcement learning, of a reinforcement learning algorithm, is to, is to play the game, and the formalization of that uses this reward signal. So we have this notion J. J here it's called the return, and the idea is, I'm unrolling my system for capital H steps. I'm going to look at the average reward for H steps. I'm going to take the expectation with respect to this random variable, and then I'm interested in long term, so I'm just setting the horizon to be very large. And what this thing models is the average reward I'm getting as I move in that MDP. And the goal of traditional reinforcement learning is to find the optimal policy. So this is traditionally denoted as pi star, and pi star is just defined as the policy that gives me the maximum return, the maximum expected average reward. And so now let's become slightly more concrete. So we have all these things that we think our Minecraft bot should do. It should do interesting things. It should not take too long, not too short to solve a task. It should walk without jitter naturally. It should be able to navigate to the opposite end of the map. And we're trying to accomplish these things using this formalism that we have. We have an agent, we have a reinforcement learning agent that's just trying to maximize these rewards. And what happens is we see, there's a problem here, because it's difficult to define a function from states to actions to real numbers that talks about, walking naturally. What does it mean to walk naturally? What number do I use to differentiate a natural walk from a non-natural walk? It's not easy to say. And so the problem with standard reinforcement learning is that specifying rewards is challenging. It's not easy to describe what we want. So in many practical problems, it's much easier to provide a demonstration. And moreover, there's a second problem with standard reinforcement learning. Even if somehow we know what the right reward is for our setting, the problem with reinforcement learning is that it sometimes just fails to discover the interesting states. There's this problem in reinforcement learning, which is called exploration. And there's been huge amounts of progress in exploration, and reinforcement learning methods are getting better and better. But the thing is that exploration in many practical settings is still very hard. And we had this desideratum about the Minecraft bot that it is supposed to be able to navigate to the opposite side of the map, and that type of challenge is still very hard to get right with modern reinforcement learning. So the thing we're going to talk about in this talk is called imitation learning, and it's a way to maybe not address, but at least sidestep these two problems with standard reinforcement learning. So just to recap, because I think it's a really important slide in this talk. Specifying rewards is hard because we don't know what things like a natural walk mean. We do not know what it means to maximize happiness, for instance. And moreover, exploration is hard, and exploration is crucial for solving practical reinforcement learning problems which involve huge state spaces, huge action spaces. So we're going to sidestep these issues by using imitation learning. And so now, once we do imitation learning, we again look at the list of things that we want our agents to do. We want it to take not too long, not too short. We want it to walk naturally without jitter. We want it to navigate to the opposite end of the map. And now we have a way to tackle this problem, because we can just ask someone, well, can you just do this? Can you show me what you mean by natural? Can you show me what you mean by not too long, not too short? Can you actually show me to navigate this huge map so I don't have to discover, the 10,000 steps that take me there? And that is the core idea and the core motivation of imitation learning. So what is imitation learning? So in imitation learning, we have an expert. So an expert is someone who works really hard playing Minecraft and providing these trajectories that we want to train off. So what we do is someone plays the game, we get the data. So the data is, what the expert is doing in a certain state. What is the expert doing to accomplish that natural, nice behavior that we want to see? And then we're going to take that data and we're going to turn it into a policy. Just to recap, a policy in reinforcement learning is a mapping from states to probability distributions over actions. And moreover, there is an additional there's an additional issue here, which is really important for many imitation learning algorithms. So optionally, when we do imitation learning, we can use a feedback loop. So some imitation learning methods still use this mechanism that we first saw when we introduced imitation learning. So I still have actions, and I'm still seeing some state, and I'm still moving in this Minecraft world. But the crucial difference between imitation learning and standard reinforcement learning is that there's no reward here, right? Reward isn't used. I don't have access to what the expert was trying to maximize or what the expert thought they were doing. I just have states and actions. I do not have rewards. And so there's going to be imitation learning methods that just use this. They take data and convert them to a policy. And there's going to be imitation learning methods that also use this loop. And we're going to see examples later on in the talk. Another point that I really wanted to stress, because it's crucial for making imitation learning work, is this notion of observability. So we have, when we introduced our formalism, we were talking about this Markov decision process, the average reward version. And just to recap, when we introduce an MDP, we assume that the state is Markov. I know it's tautological, but I'm stressing this point because it's really important. And what it means is the future behavior of a system depends on a current state. It does not depend on the history of past states that I saw beforehand. Moreover, we're making two assumptions. So the state space and the action space are the same between the expert and the imitation learner. It is not the only setting in which you can consider imitation learning. It is, in fact, all these assumptions can be relaxed. But for the sake of simplicity, this is the setting which I think encapsulates the essential complexity of the problem while still being tractable. And that's why I feel it's useful to address in this talk. Okay, so in other words, just to recap, both the expert and the imitation learner have a policy, which is a mapping from the set of states to probability distributions over actions. Okay, so let's show a plan. So the plan is we're going to do in stages. First, I'm going to talk about behavioral cloning. Behavioral cloning is a really simple imitation learning algorithm that you can implement in 6 lines of code. And it is, despite its simplicity, very useful. And then we're going to talk about more advanced methods. So I'm going to do that in 2 stages. First, I'm going to talk about a technology which is called inverse reinforcement learning. And afterwards, I'm going to talk about adversarial imitation learning, which is kind of the, one of the most sophisticated methods that exist today for tackling this problem. And after that, we're just going to summarize what we've learned. And I'm going to talk about what next steps you can take to teach yourself more about imitation learning and to do your own research in the field if you want to. So just to recap, our goal in this tutorial is that you understand the basics and know where to look for more. It is not my goal to give a review of every paper in imitation learning. In fact, that has appeared over the last 20 years or so. In fact, that would be impossible because that field has grown so large that we are kind of forced to make to select a very small subset of algorithms, which I think are really canonical. Okay, cool. So I guess let's move on to our first algorithm, which is called behavioral cloning. Behavioral cloning is a simple imitation learning baseline. It often works really well, and the reason I'm focusing on it so much is that behavioral cloning has a little bit of a bad rap in the community. So I kind of wanted to address that point and explain in which cases you can use it and in which cases you shouldn't use it. Okay, so let's talk about behavioral cloning. So just as a recap, let us go back to the definition of what imitation learning is. We have this expert. The expert is working hard playing Minecraft, right? And they give us this data set. And a data set contains, in that state I do this action, and in that state I do that action, and so on. And we're going to take that data set and we're going to convert it to policy, and we're going to use that policy to play Minecraft. And in this particular method, behavioral cloning, I'm not using this loop, right? So this crossed out loop means I'm not using it in this algorithm. I can still use it in other algorithms. So it's going to be really a very simple thing. We're gonna take the expert data, we're gonna convert it to a policy, and then we're gonna do the simplest thing possible. And the simplest thing possible in this case is just supervised learning. Okay. So let us provide some more detail about that. So first, let me talk about the concept of maximum likelihood. Maximum likelihood is a concept which is central to traditional statistics, and behavioral cloning is a way of applying that concept to imitation learning. So, we know that when I have a policy, we've seen in this introduction about MDPs that we started the talk with, once I have a policy, I can roll it out in the MDP and I can generate trajectories. And when I have trajectories a random variable, because both my policy and my environment is stochastic. So I can think about, this random variable has a density. And I can use this density to define a likelihood. And now the idea of behavioral cloning is really very simple. What I'm going to do is I'm going to look at the probability of seeing that trajectory, and I'm going to find a policy which maximizes that probability, right? It's very simple. I'm defining probability of something. I'm looking for a value of a parameter which maximizes that probability. And I can use a log because log is an increasing function, so it doesn't change anything in terms of the optimum of a problem I have. And maximum likelihood is a very old concept. It was introduced by Ronald Fisher in 1912. And it's an old concept. It's a very powerful concept and still used very often in machine learning. Now, of course, I do not intend to say in this talk that this is the only thing around. There's Bayesian statistics. There's ways of doing things which are very different and also more powerful in certain ways. But this thing is very simple and works in a lot of practical cases. So I feel it's worth paying attention to. All right, so let us take a look into how exactly we can use maximum likelihood to do imitation learning. So in the first line in this slide, what I'm going to do is I'm going to find the parameters of a policy to maximize the likelihood of seeing the trajectory. Tau is the trajectory. And the way the trajectories come into this algorithm is the expert just provided me a trajectory. They play in Minecraft, they saved the data set, the trajectory is my data set. I'm maximizing the likelihood of that data set by changing the parameters of my policy. And then the thing is that we assume that our system is Markov. So the probability of seeing a trajectory, I can define as a product of probability of seeing the initial state, right? Probability of executing an action given a state, probability of going to the next state conditioned on the state I am and the action I've just chosen, and then I just aggregate that over the time steps. And the reason it's a sum here is we're working with log probability. So the product is turned into a sum, right? So we have a sum along the trajectory. And now, as you can see, we're doing an argmax over the policy parameters. So I'm picking a theta to maximize the likelihood of the expert trajectory under my policy. And these terms here, the P0 and the transition model, do not depend on a policy because this is not something I can influence. I'm given the Minecraft game in our example, in our metaphor that we started our talk with is given. I cannot do anything to change the transitions. I can just change the policy. So I'm just going to ignore these terms because they do not change the value of the argmax, right? So under an argmax, I can add any constant I want, and I still get the same solution. And then what we get is we just maximize a policy so we're looking for a policy which maximizes this term. And of course, so this very simple derivation just uses one trajectory. But of course, we can do this with multiple trajectories. And of course, the way we do that is just we sum the likelihoods, sum the log likelihoods, sorry, because the trajectories are IID, right? So if I have an IID random variables, then I can write the likelihood as a product over the individual trajectories. Okay, so let us see, how does it work in practice? How can we implement this algorithm? So the good news here is that because maximum likelihood is so powerful, in fact, to digress a bit, the machine learning community recently has done a lot of work on very complex models for natural language, right? And all these models for natural language, all this fancy stuff that's happening, with language modeling, with modeling a density over sentences. All that work uses maximum likelihood, and the graph neural networks use maximum likelihood as well. So coming back to this point, maximum likelihood is exactly what machine learning frameworks are optimized to do because it's so popular, and therefore it's really simple to implement. So if we go back to imitation learning, where our state is 5-dimensional, and we have just 2 actions, it's a binary, so my action at a given state is either 0 or 1, then in this slide, I can fit a torch implementation of maximum likelihood, right? So I'm going to define my policy to be a linear layer and a softmax layer. And then, so this is, I'm defining my softmax layer, I'm defining my linear layer, I'm defining my policy to be a composite. I'm taking the softmax function of the linear layer of the state. I'm defining my loss for its negative log likelihood. And then I'm just saying, well, I am computing the loss of the policy that I'm trying to model over the actions that the expert has provided me, and I'm going to backpropagate it, right? And the reason it's so simple is because people have put in a lot of effort in terms of software engineering to make maximizing log likelihood easy, right? Because it's so popular. Okay, cool. So, we started with this list of things that we want. We want to have a behavior which doesn't take too long and doesn't take too short. We want to work naturally. We want to navigate the opposite end of the map. Well, is that it? Have we solved the problem? Is there anything more? And turns out that there is quite a bit more, and that is because that very simple method has issues, and things can go wrong. And the purpose of this slide here is to explain, the class of situations in which things do go wrong. The example I'm using is taken from this paper by Ross and Bagnell, which is, I'm also going to provide the literature list at the end of the tutorial. This is a very classic paper in imitation learning and very worth reading. So the general idea is I have an expert, and the expert is, I have 3 states in this system. So in S0, the expert is taking this state A1. In S1, the expert is taking A2. In S2, the expert is taking A2. And now I'm learning my policy using behavioral cloning. So I have a lot of data from that expert. I want to imitate the expert. And the thing is that when I solve machine learning problems, there's always some probability of errors. So when someone says the accuracy of my machine learning agent is 100% on test data, then I probably shouldn't believe that statement. There's always a small error, even if your method is very good. So when we train the imitation learner, we have to deal with the fact that we have this error that we somehow have to handle. And so consider the following. Assume that the imitation learner has learned the following policy. So in this state S0, I'm choosing the same action as the expert, the good action A1. I'm choosing it with probability 1 minus T epsilon. And in state, with the remaining probability, so that they sum to 1, I'm choosing the wrong action A2. And in the other 2 states, I managed to exactly replicate the expert. And now we're looking at trajectories of length capital T. So now the thing is that along the trajectory, the average misclassification error is epsilon, right? Because I'm making error T times epsilon in the first state, and I'm making absolutely no error. I'm making 0 error in the remaining states. So on average, as I average the errors along the whole trajectory, I'm making epsilon error. And so the thing is, let's look about what the rewards are. Let's look into what the expert rewards are in that system. So let's say the reward of S1 is 0, the reward of S2 is -1, the reward of S0 is 0. So the expert return is 0 because they never go into that branch. The return of the imitation learner is, now with probability T epsilon, I'm going to get this, right? It is because I'm T -1 times, I'm harvesting this -1 here. And so I have this term. And now let us do some math on that term to see why that's bad. So just to recap, the return of the expert, the return of the imitation learner is so the sum of the rewards of the expected sum of rewards of the imitation learner is given by this term. The expected sum of rewards of the expert is 0 because the expert doesn't make mistakes. And now if we look at the per step return, right? So if we divide by the length of a trajectory, so per step, what is happening is I'm getting an error because I had the square term here. Now I have a per step error, which is t times epsilon, and it's really bad because what this mathematical model tells me is a small error of epsilon per step in fitting the policy results in a per step error of t times epsilon in the return. And the return in reinforcement learning is what I ultimately care about. So I'm paying for long-term consequences. A small mistake in the beginning causes a huge difference in return at the end. And that example tells us that we should be really careful applying supervised learning theory to imitation learning. Okay, so however, because, as I said, behavioral cloning has a bit of a bad rap, I just wanted to say, don't give up on behavioral cloning. The example in the previous slide holds. However, in many practical MDPs, it is possible to recover from mistakes, and in fact, you have data on how to recover. So if we go back to this original example, which breaks behavioral cloning, what we can do is we can initialize the expert in this state, right? And initially, what happened was the expert was taking A2 in that state. And the reason the expert was allowed to take A2 in that state is they never visited it, so it didn't matter, right? It didn't influence the return they were getting. But if I force to initialize the expert here, if I go and say, well, dear expert, now you're in that state, please tell me what to do. So the expert will provide will tell me that actually I should execute A1 and I will be able to recover and I will be able to go to that branch. And of course, the thing is that it requires data. I have to go to the expert and ask them and, and say, well, please provide that data. And once I have that data, behavioral cloning on this new bigger data set will work. So the conclusion here is that if I have enough data, then behavioral cloning can be made to work. Okay, so the expert is gonna, once I force it to be initialized in that state, the expert is gonna pick that action. Okay, so we've covered behavioral cloning. Now let me talk about another type of imitation learning, which is called inverse reinforcement learning. And inverse reinforcement learning is also known as imitation learning with intrinsic rewards. Intrinsic is a word which roughly means I'm making the rewards up. I'm constructing them myself rather than obtaining them from someone who's specifying the problem for me. So let's go back to the general architecture of imitation learning. We get the expert is playing Minecraft, the expert is providing a data set. My goal is to turn that data set into a policy, which is a mapping from states to distributions over actions. And in that method, I am going to use the feedback loop. So I'm going to have this interaction between the environment and the agent, and I'm going to send the actions to the environment and get states from the environment. Reward isn't used. So I will be using intrinsic reward, but I'm not going to be using the extrinsic reward. The thing that the expert is maximizing. All right. So, let's come up with that reward. So first thing that you have in mind is, well, we don't observe the expert reward, so maybe we can reconstruct it. Maybe, we can just assume that the expert is maximizing some reward, and maybe we can just recover it from, knowing how often the expert visits a certain state action pair. So we have this expert data set. It says, the expert is in that state. It's taking that action. And the way it works is, we can model that as a probability density. And so, that value is going to be larger if the expert visits that state action pair a lot, and it's going to be small if the expert does not visit that state action pair. And our goal is to reconstruct the expert reward. And the first question that we ask, is it even possible? So clearly, if I have a reinforcement learning agent, I have a reward, and then I multiply all my rewards by 2, then I'm going to get the same behavior, right? This distribution of state action pairs is going to be exactly the same for one as it is for the other. So what can happen? So what can we do to solve that problem? Clearly, if two different reward signals lead to the same distribution over state action pairs, then I cannot take that distribution and recover the original reward, right? So I have that problem. It's ill-posed in that sense. But actually, what happens that it's not just scaling that is a problem. It is a worse problem. So now let's think about an MDP which only has one state. And MDPs like that are called bandits. And let's say that the distribution of expert data is that I'm always taking action 2 and I'm never taking any other action, right? And now I'm assuming that the expert is maximizing some reward. And our question is, can we recover that reward just by knowing these probabilities? And the problem is that, all we can deduce is that action 2 is better than the other actions, but we don't know. Other than that, we don't know what these values are. So what this example teaches us is that it's not just scaling that's a problem. We cannot hope to extract the expert reward just from seeing which states the expert visits. And therefore, we have to do something else, right? So we cannot reconstruct the expert reward, but what we do instead is we're going to come up with a reward that leads to behavior that matches the expert, right? And in a way, that's enough, because in imitation learning, we care about reproducing expert's behavior. We don't directly care about reproducing their reward. Okay, so let's see how we can do that. So in apprenticeship learning, which is the particular method of inverse reinforcement learning, that I'm going to talk about in this tutorial, the assumption is that this ground true expert reward, which we don't know, has linear structure. So I'm assuming that the reward as a function of state can be written as a dot product between some weight vector and some feature vector, which depends on state. And I'm assuming that the weights are reasonable, meaning not too large. And then once I know that the reward is a dot product, I know that a value function in an MDP is just a sum of rewards over time. So I have a sum, I have an expectation, which is a linear operator, and then I have a dot product inside. And because all these things are linear, I can just pull out the dot product. And what I get is that a value function is a dot product between this weight vector W and an expectation over features, right? And because the return is just a type of a value function, then this holds for the return as well. And I just wanted to stress one important thing about this. So when I said it's linear, the linearity is in the features. Each feature, phi of s, can be a nonlinear function of state. So the setup here is similar to linear regression. Okay, so let me talk about how the algorithm works. So, well, the general structure of the algorithm is that I'm going to make intrinsic rewards so that the expert does well and the existing policies do poorly. And then I'm going to call a reinforcement learning solver, which maximizes these intrinsic rewards. And the resulting policy is going to be closer to what the expert is doing. So the algorithm is going to interleave these two steps. I'm going to interleave the part where I train the policy and construct a reward with a part, I'm going to interleave the part when I train a policy with a part where I construct a reward. And the algorithm, and on the algorithmic side, the thing looks like this. So in the step where I make the intrinsic reward, I'm solving and I'm solving an optimization problem, right? So we assumed when we introduced the algorithm that the rewards are linear, right? So the rewards are linear in the features of state that we know. And so the way I construct the reward, all I need to do is I need to find this feature vector W star. So I'm defining the W star that I want as an argmax of weights which are of reasonable size. Of the worst case, so this min here means a worst case difference between the expert. This thing is the expert return because we're taking trajectories that come from the expert distribution. So this is the expert return, W times this expected feature, minus the W transposed dot product, the expected feature under my JAVE policy. So the meaning of this equation here is I want a reward so that the expert does well, where this is large, and the existing policies do badly. This is small, and I'm taking the worst case among the existing policies that I have. And so I have that W star. And now the question is, once I have that reward, what do I do with it? So I call the RL solver. And because I assumed everything is linear, the reward of state is just this W star that I have dot product feature of a state. And I'm going to call the reinforcement learning solver, which is the place where I'm using this feedback loop, which we mentioned when we introduced imitation learning. And I'm going to obtain the next policy. So I'm just going to call that policy pi_t. And the next time I make up an intrinsic reward, when I do this minimization inside this problem, I'm going to add that policy as well. So this minimization is among all the past policies that I have seen. And well, you might say this expression looks a little bit weird, right? So the general idea, this is not a mathematical proof, but we can think of it conceptually. What this algorithm is trying to do is come up with rewards such that the behavior gets shifted to a situation where this term becomes small, right? So we're seeing little difference in the end once we run this many times between the expert behavior and the behavior of the policy that we have. And you might think, well, why does it make sense to minimize that difference? And the idea here is called feature matching, and it's not specific to apprenticeship learning. And let me just provide a very short explanation of why feature matching makes sense. So if we write the expert return and the return of the imitation learner, and we look at this difference between these two things, so we have a difference in expectations. And then we want to pull the W out of this absolute value. And the reason we can do this is there's a very well-known inequality in mathematics known as Cauchy-Schwarz, which talks about the relationship between dot products and norms. And so we can use that, and we can get this inequality. And then because we assumed that our weights are small, so we assumed that the 2 norm of W is less than 1, this is actually less than the difference in these aggregate features. So this expression is sometimes called the successive feature. And so the justification for that algorithm that I've shown in the last slide is that, well, that algorithm gives us a situation where at the end of the iteration we have this term is small, right? And if this term is small, then we know that the difference between the return expert is getting and the return the imitation learning agent is getting is also small. And that is basically what makes this algorithm work. Okay, so let me just provide a summary of how apprenticeship learning works. So this problem, we haven't discussed it, but we so we haven't shown it formally, but the optimization problem that we had in this step that generates the reward in this algorithm is known as convex optimization. So just as a recap, we can divide functions as into functions which are convex and functions which are non-convex. And convex functions have the useful property that if I find if I have a convex function, that then any local optimum I can find is also a global optimum. And moreover, convex functions have a property that they are really easy to optimize. So there are very good results about optimization algorithms, variants of gradient descent, for example, that allow me to optimize convex functions really fast. So when you want to implement this algorithm, all you need is to have a solver for convex optimization problems. And that is because the solution, it is clear how to get the right solution to that optimization problem. It is something that is easy to debug. Unlike the more sophisticated algorithms which use deep learning, where we have to do non-convex optimization. And I just wanted to say that, there's one more thing. Actually, the optimization problem in this algorithm is an instance of a technology which is known as a support vector machine. So I didn't explain the link in this slide, but I will give you a reference to the paper afterwards, and you can look it in a paper. And the optimization we're doing is exactly the support vector machine optimization. And because of that, you can use a lot of existing software to solve that optimization problem. And because support vector machines have been around for a while, that software is very mature. So it's something that is, if you care about stability, then it is something which is, well worth looking into. So just to recap, the setup here is that we assumed that we have linear features, and the assumption here is that someone provides us features which we already know are good, and then the reward function is linear in these features. And another thing I wanted to mention about this algorithm is that despite it has this linear formulation, and despite it is, it's a pretty simple, it's also a precursor of more modern imitation learning algorithms, one of which I'm going to talk about in a later part of this tutorial. And because of that, it's kind of worth understanding this before you go into the more modern algorithms. Okay, cool. So I guess we are 1 minute ahead of time. I feel it would be a good time to take questions. All right. So let's go.
Yeah, so we have one question. So what does it mean to have different policies?
All right. So the general idea is that a policy in reinforcement learning just means a behavior. So different policies means I have different behaviors in my system. And I actually wanted to follow up on this question. Was it specifically about apprenticeship learning, or was it just a general question about different policies?
In apprenticeship learning.
Okay, so the algorithm is an iteration. So each time I'm generating a reward, and then this reward is something that I'm calling my RL agent to solve, and that agent gives me a policy. And so after I've run the algorithm for n steps, I have n policies.
And shouldn't the policy be somehow determined by the reward?
Yeah, so the way that the reinforcement learning black box works is I give it the reward, and then the black box computes a policy which maximizes the return, which is relative to that reward. So the return is defined as a sum of rewards over time. And so as I use different rewards, I'm going to get different optimal policy because I'm maximizing a different objective. And at each time step, the RL algorithm is trying to maximize the total cumulative reward that is given at that time step. And it produces a policy. And then I'm feeding that policy to this inverse RL step, which comes up with the next reward. And then that next reward, I'm calling the RL algorithm again. And so I keep iterating on and on and on until I have a policy which matches the features of the expert, at which point I can stop.
And are you aware of any difficulties in training an actor critic of policy using some kind of correlation, for example, bit trace? It may be big variance, low convergence, etc.
So in this apprenticeship learning tutorial, we assumed linear features, and I think with linear features, RL is actually pretty stable. If we have good linear features, which we don't have to learn online. If we move to the setup of deep reinforcement learning, an actor critic setup in that space, it is, basically it's a difficult optimization problem. It's very non-convex. We're not guaranteed to find the right solution, and it's not easy to stabilize, but it is possible to stabilize. And so right now my answer is not specific to apprenticeship learning. It's more about reinforcement learning, deep reinforcement learning in general. The kind of traditional way of stabilizing an actor critic method is you use a target network in a critic. And the idea is that you have an actor that tries to maximize the critic, and you have a critic which you bootstrap off the values of a critic obtained at past iterations, and you want to make that bootstrapping as close as possible to supervised learning. And then if your learning rate is small enough and your targets change slowly enough, then yes, you can stabilize actor critic, although it is not, in practice, it's not always easy to do.
Well, it seems these are all the questions we have at the moment. We can have a 5 minutes break and then we can continue at 2 p.m.
All right, cool. Thank you very much. So let's continue at 2 p.m.
Yes. And Camille, is sufficient if you just mute your audio feed and also as well as the camera feed, you can turn it off and we can continue at 2 p.m. So it's again now 2 p.m. Kamil, if you're ready, we can continue.
All right, thanks a lot. So I think we can continue. Okay, so in this part of the talk, I'm going to discuss adversarial imitation learning. It's a very powerful type of imitation learning algorithm which works by minimizing divergences. So let me go into the details. So let's take another view at imitation learning now. Let's consider a Markov decision process, and we have this view that the expert gives us some distribution over state action pairs. So we have this probability of seeing S and A under the expert policy. And our imitation learning policy, the thing that we're trying to learn, also produces some distribution over state action pairs, right? And the idea of adversarial imitation learning is very simple, but very powerful, which is going to change the parameters of a policy to make the divergence between these two distributions small. So I'm solving an optimization problem. I'm minimizing the parameters of my imitation learning, and I'm minimizing them so as to make the divergence between the expert distribution of state action pairs and the RL distribution of state action pairs. So I want to make that divergence small. And you might ask, well, haven't I seen it somewhere? It is, and of course, this is the very same idea as generative adversarial network, which is a very powerful model for learning generative models of probability distributions that has become hugely popular in the machine learning community. So, well, let me go a little bit into the difference between, the ways in which adversarial imitation learning is different from a GAN, as well as ways in which it is similar. And we're going to, I know that, you're waiting for me to define the actual algorithm, so we'll define the algorithm later. But for now, let's just talk about the comparison with GANs. So let us look at a generator network. So in a regular GAN, what is happening is I have some noise vector, which can be uniform noise or some noise from a standard normal distribution or some other simple family that I know. And I'm going to push that noise through a neural network, and I'm going to generate samples. Don't worry if you don't know about GANs. The idea, so the core idea of doing this ancestral sampling to generate these things is actually it's very powerful, but it's also very easy. So what happens is I'm taking some IID noise, I'm pushing it through the generator network, and I'm getting a sample. And the samples in like standard literature about GANs are typically images, although they could be any object. In imitation learning, the samples we're looking at are state action pairs. So if we look more on the right-hand side of the figure, this is the equivalent picture for when we do adversarial imitation learning. So we start with IID noise. We put the IID noise into our policy. The policy is allowed to be stochastic. So policy is a probability distribution over actions. It's not always the same actions. And I'm using that policy to generate an action, but that is not the end. That is not the end, because in imitation learning, I have this environment. So I send my action to the environment, and the environment gives me a state. And this is how I generate the states. And the environment can be stochastic as well. So I can model stochasticity as a deterministic function. Like any random variable is I can write as a deterministic function of some noise, which comes from some simple distribution, right? So I have two sources of noise in this system, the noise that comes into the policy and the noise that goes into the environment. And the crucial difference between the right-hand side and the left-hand side is that the samples I'm getting are not independent identically distributed, right? Because this environment has state. So when you look at this picture, first time you see it, you can think of this black box around these components and say, maybe this is just some new network architecture for a generator. Maybe it is literally, again, with a different generator architecture. So the answer to that is, well, almost, but not exactly, because the samples are not IID. And that is a property which is really important for how imitation learning works, because the Markov decision process is a model of sequential problems. So sequentiality matters. It is central to the task we're solving. We cannot simply ignore it. Okay, so having looked at the generator, let us look at the discriminator. So the discriminator is the same in a regular GAN and in adversarial imitation learning. So we see a sample, and if we wanted an example from a traditional GAN literature, the sample would be an image, and we feed it to the discriminator network, and the network is telling us whether it's real or fake. And the imitation learning analogy is that rather than an image, I have a state action pair, and I'm feeding into the discriminator, and the discriminator is telling me whether the state action pair looks like it came from the expert, or whether it looks like it came from the simulator, from my imitation learning algorithm. So the mapping here is real samples are the expert samples, and the fake samples, the so-called fake samples, are the simulator samples. Okay, so we've seen the architecture for the networks. Now let's do a recap of how GAN training works. So we have to step back a little bit, and we have to ask ourselves this question, well, given two probability distributions, how do we compare them? So the most standard way to tackle this task is that we have this object, which is known as the Kullback-Leibler divergence, that it tells us how far apart are row 1 and row 2. And we can see that the Kullback-Leibler divergence is not symmetric, right? So if I swapped row 1 and row 2 in this formula, I would get a different expression. And so instead of using Kullback-Leibler divergence, we're going to use a symmetric version, which is known as the Jensen-Shannon divergence, and it's defined using the formula in the box. We're going to talk a little bit more about how to, the importance of the divergence, so, doing imitation learning with other divergences. But for now, I just wanted to settle on the Jensen-Shannon divergence, because this is the example that was introduced both in the original paper on generative adversarial networks and in the original paper on adversarial imitation learning. And so it is the most canonical choice. Okay, so first thing we do in terms of math, we're going to rewrite the Jensen-Shannon divergence as an optimization. So we settled on this formula for DJS as a way for comparing two probability distributions for 1 and row 2. And we can do a bit of math, and we can say that up to a constant, which doesn't matter because we're going to be optimizing this, the Jensen-Shannon divergence can be written as this minimization. And I'm not going to show the proof in the slides, but if you want to look at a proof, just have a look at the original GAN paper. It's a very classic paper in machine learning. It's very well worth reading. Okay, so we have this bit of math that says that this divergence I can write as this optimization problem, which involves expectations. Okay, and now the reason this is important is that this way of writing the Jensen-Shannon divergence gives me a handle on actually minimizing it in practice. This gives me a way of defining an algorithm for minimizing the Jensen-Shannon divergence. Okay, so let's start by training the discriminator. So we can define the Jensen-Shannon divergence as this problem that we saw in the last slide. And now we can interpret the terms in that expression. So the discriminator of SA, it is just, for now, let's say this is some function that takes a state action pairs, and it gives us a value between 0 and 1. And so this term is the log probability of that the data is fake. So we can think of the GAN training, the problem of training a discriminator as a classification problem between the fake data and the real data. And so this corresponds to to training a classifier to distinguish the fake data and the real data. This is the log probability of the fake data. We're sampling here from the simulator, which is what is the analogy of the fake data in adversarial imitation learning. And this is the 1 minus probability that it's fake. So it's the log probability that the data is real, and we're sampling from the expert data here. And now, so we can do this, we can solve this optimization, and it's going to train a GAN discriminator. And so we're gonna find some weights W star, and right, so in this optimization problem, we're minimizing over W, and so the optimum we're gonna call W star. And the important thing here is that for purposes of the theoretical derivation, the generator is fixed, right? So this distribution that gives me this fake data is fixed in this expression. And then when we train it, we have to make sure that the state action pairs that come out of this simulator are independent. So in traditional GANs, it's not a problem, because in traditional GANs, we're independent by definition, because the whole thing is set up as a sequence of IID random variables. Here I have the sequentiality. So the really, the thing that is absolutely correct to do is, if I generate that data, I can just take one state action pair from every trajectory and then generate my trajectory's IID, and then I have the IID data. But of course, that's very wasteful. So what happens in practice is we just use all the data from a trajectory, but we shuffle the data. And this shuffling of the data is what makes the discriminator training in adversarial imitation learning different from standard GANs. So just to repeat, standard GANs don't need that because they IID by definition. And the shuffling is not guaranteed to make the data IID, but for many MDPs which have a lot of stochasticity, which makes fast, it is enough to make this work in practice. So the practical takeaway from here, if you train your generative adversarial imitation learning, make sure to shuffle your data when you train the discriminator. Okay, so let's have a look at how to train for policy. So going back to this expression for the JS divergence, and now we're no longer minimizing over W, we've plugged in the optimal W, so we call that W star. And now the idea is, well, given W star, how do we improve the generator? So the first thing we notice in this expression is that there are many terms here that do not really depend on a policy. So the policy influences this distribution of states seen under the imitation learner. It does not influence anything here. And because we're optimizing the policy, therefore we don't really care about these terms because they're constants. And so we're just going to optimize that term. And we notice, so when we began the talk, we started with this average reward reinforcement learning formulation. And we had this equation that, this is just like if I take the long-term average reward and I take the expectation of that is my return, and that is what my reinforcement learner is trying to maximize. And so I have this expectation, and it turns out that this formula is I can just literally pattern match it, ignoring this constant, which doesn't matter for the optimization. I can pattern match this formula into this. So what it tells me is I can train the generator by solving a reinforcement learning problem. And that's great news, because I know how to solve reinforcement learning problems. There are algorithms for that. And we can see that in this equation, the expression that plays the role of the reward is this log D expression. So I'm setting my reward to our reward of SA, with the reward associated with taking action A in state S. I'm defining to be the logarithm of a probability computed by the discriminator, right? And that coincides with what we saw before. If we think about it intuitively, that thing D is large for things that come from the expert, and it's small for things that do not come from the expert. So I'm trying to encourage my reinforcement learner to go to the things which coincide with the expert, which is what imitation learning is trying to do. Okay, so now we know how to train the generator. So let's move on. So let's formulate an algorithm. Excuse me. Okay, so let's formulate the imitation learning algorithm. So we're going to interleave these two steps. We're going to train the discriminator by minimizing this expression that we've just seen. And we're going to train the generator by calling the reinforcement learning solver with these rewards. And we're going to keep iterating this, and we're going to keep iterating this for a long time. And then what you might ask, well, do we know, will it converge to something? And that turns out to be a really good question. so in general, we cannot always guarantee that adversarial imitation learning converges to a single good policy, right? What we can do, however, and what makes this algorithm really useful is that, when we have this process that alternates the training of a discriminator and the training of a generator, then in general, it will end up in some cycle. And so let's say I converge to my cycle. I'm on that cycle by time step capital T, and I'm doing capital T prime more time steps after that point. And when I get at each time step, I get a policy. And then the policy that I return is a mixture of policies along these time steps. And either I can just return that mixture, or I can optionally distill that mixture into a single policy. So adversarial imitation learning requires me at the end to, in general, I need to either I am returning a mixture or I have to go through this distillation step. However, in practice, in many practical systems, if we make assumptions on the expert, which I'm not going to talk about, we can just take the last policy from GAIL and it still works. And in practice, for the problems that we want to solve, it's very often true. If you want to have an example of a problem where it's not true, is if we want to do imitation learning in games. We can do that as well, and in that case, we end up with cycles like that, and we have to deal with these cycles. But when you implement it, the first thing you should do when you train it on simple problems is just take the last policy and it should work. Okay, so well, we've defined this algorithm, and we called it adversarial imitation learning. So let me just talk a little bit about where this name comes from. Why do we call it adversarial? Because there wasn't anything, so we've shown some math for minimizing a divergence, but we haven't really, there wasn't anything that I could really say is an adversary in that system, at least not directly. So the reason it's called adversarial is we change the policy to maximize the total expected reward, and we change the discriminator of a reward to compute the Jensen-Shannon divergence, and that computation of the JS divergence it involves a minimization. And interleaving max and min is known as a min-max problem, and it's also called a game. And I just wanted to say that the reason this is called adversarial is because we're solving a min-max problem. And this is not the same as if I had an adversary environment that is trying to prevent me from winning. So if I'm doing Minecraft, and you could imagine there's some other, I'm training the agent to do useful things, and there's some other agent in the environment, and the other agent is trying to make me lose. They're doing, they're doing mischief. And that is not the meaning of adversarial that is used in that algorithm. You could have algorithms that try to cope with that, but that's a totally different branch of algorithms. So I just wanted to stress that the meaning of adversarial in adversarial imitation learning concerns the type of optimization we're doing. The optimization process is a GAN, it's a min-max problem. Okay, cool. So let me move on. There's a link between adversarial imitation learning and inverse reinforcement learning. So we had this discussion earlier that, how do I make up a reward given expert data? And that idea, of course, is not specific to GAIL. We've seen it earlier. Just to recap, we're training a generator by calling a reinforcement learning solver, and we're calling that IRL solver with rewards, which are the log of the discriminator. And I know that this is simple, but this idea of making up rewards as we go and making the rewards encourage the reinforcement learning agent to converge to the right policy is very powerful, and that's why I'm stressing it so much in this talk. Okay, so we can, we've kind of seen the basic version of GAIL, and now what we can look at is we can look at an extension. So we have when we introduced GAIL, we were looking at this problem of how do I minimize the divergence between two distributions. And in the example we had with distributions, that we were tackling were the distributions over state action pairs. So I was looking at a divergence DJS between row 1 of SA and row 2 of SA. And what we can do instead is we can do imitation learning when we just have the states. We do not have the actions. So instead of minimizing the divergence between the distributions of state action pairs from the expert and the agent, I'm going to do something different. I'm going to minimize the divergence between the distribution of state tuples. So I have two states, and the tuple consists of my state at this time step and my state at this successor state. And I'm going to minimize that divergence. And so the good news here is that the algorithm I get is almost the same as regular GAIL we've seen. So I'm not going to write it down, but the only difference when you actually implement it is the thing that goes into the discriminator. So in a standard GAIL, when I have a discriminator network, the thing that goes in is the state action pair. Here, the thing that goes in is the tuple of state successor state. And I can still do the same thing, and I can still recover a good policy. And the reason I mentioned that it's really cool, and you can think of it as, if we forget, so Minecraft is great, but if we wanted to look at another example for the time being, then let's look at driving. So I'm learning to drive, and I am not seeing what the driver is like, whether they are braking or accelerating or like turning the steering wheel. I'm not seeing that. I'm just seeing where the car is going. So I'm only seeing the state. I'm not seeing the action that the driver of the car is taking. And still I can imitate the driver. So that that allows me to deploy imitation learning in settings where I do not have these actions, because maybe I already have a data set, and the data set just does not have actions. Maybe the expert is using a completely different action space, because maybe the expert is driving the car using the steering wheel and the pedals in the car, and the agent I'm training has different set of controls. It's just some abstract variable, some number that I pick, but has no direct relevance for the steering wheel. And so that allows me to address settings like that using imitation learning. And this is one of the reasons why adversarial imitation learning is so powerful. The fact that I can address setups such as this one. Okay, but you may ask, well, on the other hand, isn't that overkill? Isn't that a problem which is just very hard? And a problem with generative adversarial imitation learning, it's hard to implement, and it's hard to get to work on a particular problem. And it comes from kind of two reasons. So first of all, GANs themselves are hard to stabilize. So there has been a lot of progress in GAN literature, and I really appreciate the people who work on GANs and who make GAN training more scalable. But still, this is a hard optimization problem. We are computing something which is not the gradient of any function, if we think about this tuple of generated discriminator. So that's very brittle, and that requires careful hand tuning of learning rates and careful hand tuning of optimization parameters to make it work. And the other thing that we have in adversarial imitation learning is the RL black box. We're calling RL using this made up reward, and the RL has to work. So the most successful branch of RL methods, maybe I don't want to say most successful, but one of the most successful branches of RL methods are actor-critic methods. And this is kind of the type of RL that is the most commonly used in connection with adversarial imitation learning. They are also really hard, because inside the algorithm, I have two components. I have an actor and a critic, and the actor is chasing the critic, and a critic is changing in response to the actor. And this talk is not about actor critics. I'm not going to cover that. But this is on itself, having maintaining the right relationship between the actor and the critic in an actor-critic algorithm is on itself a hard task. And I think that was actually one of the questions that got asked after the first part of the talk. So whoever asked that question, thanks for that. So now the problem with GAIL is, we have two hard problems, GANs and actor-critic, and they're both hard to stabilize. And now we combine two hard problems and make an even harder problem. And we get a powerful algorithm, but it comes at this cost that training is hard, and ensuring that we converge it can be done, but it requires a lot of careful engineering. So question is, well, do we really need GAIL for imitation? And the answer to that depends on your particular use case. Very often, it is not necessary. So I just wanted to kind of keep stressing that point, because what people sometimes end up with is they think that, they look at a sequence in which the algorithms were published, and GAIL is the last and most powerful algorithm, and they say, well, I'm just going to use the best thing ever. This is the latest, the best, and I'm going to use that. And I just wanted to say, that's great. GAIL is powerful. It's a great algorithm. But if you just want something simple that works quickly, maybe you should also consider other options. Okay. So let me move on. When we were introducing GAIL, we had this conversation about the Jensen-Shannon divergence. And so we started with JS because it's what is used in the original GAN paper and in the original GAIL paper. And so I will give a pointer to the original paper about adversarial imitation learning at the end of the talk. And actually, it turns out that the choice of Jensen-Shannon is incidental. It is not, we could use another divergence and it would still work. So in practice, what happens is any divergence which guarantees that if the divergence is 0, that the policies are, that the distributions are the same could be used. And if you think about it, it kind of makes sense, because ultimately what we care about is making the distributions of states under the expert the same as the distribution of states, state action pairs under the imitation learner. And so if the divergence is 0, then they are the same. This is what we want. And within this property, there are many divergences that satisfy that. And so the choice is somewhat arbitrary. The original setup in the GAN paper for choosing the Jensen-Shannon divergence was that it has this really nice interpretation in terms of a classification problem. So if I use Jensen-Shannon, then I have this property in terms of the minimization that we had in the previous slides. And then I can say, well, training a discriminator is, I'm distinguishing real from fake. I'm distinguishing the expert from the simulator. If I used a different divergence that I can also write an optimization problem, I can also solve it using an algorithm which is very similar, just uses a slightly different equation. But then the thing is, I lose that interpretation. So I can no longer say the discriminator is classifying between expert and fake. The discriminator is just solving some abstract optimization. For imitation learning, there is currently no study about which divergence works best. So the most successful work is, so the most empirically successful work is based on the Wasserstein divergence, which is something we're not covering in this talk. If you want to, so the earliest paper I know that uses Wasserstein divergence for imitation learning is known as InfoGAIL, and you can look it up if you want to. If you're interested more broadly into the question of, which divergence should I use, what is the best divergence, a good reference for that for GANs is the Afghan paper. So do have a look at that. The general takeaway that you can draw from this paper is that the important thing for picking the divergence is how easy it is to optimize. The reality is that the optimizers that we currently have in deep learning are just not very good for the types of problems that we are tackling. And so the question of whether I'm able to minimize divergence becomes much more important than the properties of the divergence itself, right? The properties of, they don't matter that much as long as I can ensure this basic property that, if the divergence is 0, then the distributions are the same. So, yeah, so I just wanted to, if you want, there's the Afghan paper discusses several. So it's KL, it's Jensen-Shannon, it's reverse KL, it's other things as well. And if you're interested in that, do have a look at that. Another thing that I wanted to mention is the relationship between behavioral cloning, the simplest algorithm, and the divergence minimization algorithm, which is the most complicated algorithm we kind of covered in this tutorial. So let me just recap the definition of KL that we have seen in the earlier slide. So I have this expression involving the logarithm, and I can write this expression using a one term minus the other term. And what this simple equality, which is really very fundamental, tells me is that actually minimizing the KL divergence of two distributions. The reason I used variable z here is that these distributions, this slide holds for anything. So Z can be anything in that slide. I just have two distributions. I have a KL between any two distributions. I can always write it in that way. And then it turns out that, if I am optimizing the parameters of row 2, then if I take the gradient to minimize the KL, then this term disappears because it doesn't depend on row 2, right? So this thing disappears. And this thing is exactly the same as maximum likelihood. So there's a very well-known property of maximum likelihood algorithm. Maximizing the likelihood doing ML estimation is the same as minimizing the KL divergence. And that's because that thing is a formula for maximum likelihood, and that thing does not depend on row 2. And so, well, you might ask, we know that behavioral cloning is maximum likelihood because the way we started this tutorial is, we talked about how Fisher introduced maximum likelihood and how BC is just supervised learning. And so, well, if behavioral cloning is maximizing likelihood, and if maximizing likelihood is minimizing the KL, then is behavioral cloning just minimizing the KL? And it turns out, yes, it is. Yes, it is. It's minimizing the KL. But there's an important difference. So the KL that behavioral cloning is minimizing is between distributions over trajectories, right? So we might ask, what is this relationship between behavioral cloning and generative adversarial imitation learning? So to recap, behavioral cloning minimizes KL, but this is the KL between the trajectories under the expert and the trajectories under the imitation learner. Behavioral cloning does not minimize the KL divergence between the state action pairs generated by the expert and the state action pairs generated by the imitation learner. So the second type is what GAIL uses, right? So it seems like a small difference in math, but it's actually a huge difference computationally, right? Computationally, behavioral cloning is this super simple thing that I can implement in 6 lines, and GAIL is this like really complicated thing that I have to go through all the GAN stuff to get to work. So it's massively important, this question of the divergence exactly between which distributions I'm minimizing. KL minimizes the KL between the distribution of the expert trajectories and distribution of the imitation trajectories. The generative adversarial imitation learning minimize the divergences between the state action pairs generated by the expert and state action pairs generated by the imitation learner. And you might ask, well, okay, but if I just took GAIL and I used KL instead of Jensen-Shannon, right? So I mentioned earlier that, there's this Afghan paper that talks about various divergences that you can plug into a GAN and how they work and how they differ. And you can do that, and you're not going to get behavioral cloning. I just wanted to stress that you're just going to get an algorithm which minimizes the KL divergence between the distribution of state action pairs from the expert and the distribution of state action pairs from the imitation learner. And that algorithm is going to do okay. The question becomes, how easy is it to optimize that divergence? The Afghan paper has a discussion about that, and the discussion is that actually the KL is not that easy to optimize in a GAN setting because the optimization involves computing gradients of exponential functions. But that is purely a numerical issue. That's not a fundamental issue. So I guess the thing that is the most important takeaway from this slide, the thing that I'm stressing is that, these things are not the same. Behavioral cloning really is different from generative adversarial imitation learning. And I do not get behavioral cloning simply by using KL and GAIL. So behavioral cloning is not an adversarial imitation learning algorithm in a sense GAIL is. And the reason, again, I'm hammering this point down so hard is because both of these algorithms are really useful. Both of these have they are very widely applicable, and I think that understanding this connection is really important. Okay, so let me summarize the tutorial and give you some pointers about what to do when you want to do more imitation learning on yourself. And basically the idea is you should be able, after listening to that tutorial, to know where to look for more information and to kind of have a rough overview of what's happening in a field. So First of all, let me just do the comparison of the imitation learning algorithms that we have discussed. So we discussed 3 algorithms, and the algorithms were chosen to kind of give you an overview of things that you can do at different levels of complexity, to match the kind of complexity that you have in your particular problem. So we started with behavioral cloning. Behavioral cloning is something which is really, really easy to implement. So just to recap, the implementation of behavioral cloning, 6 lines of PyTorch, very simple, a supervised learning problem. You can do it in, under 1 hour. And that includes a lot of downtime. The weak points of behavioral cloning is that you need a lot of data to do behavioral cloning. And, ideally you're in a situation where you can add data if it doesn't work. If you are in this setup where, maybe the number of dimensions in your system isn't too large, the state space is small, action space is small, you can just do behavioral cloning, and you should not be discouraged by the example I've shown earlier in the tutorial, because the thing is you can just solve that, you can just brute force that problem with data and it works. But the weak point is, sometimes you just don't have that data, and in that case you have to do something else. So next thing, to try apprenticeship learning. The implementation is easy because there's a ton of work out there about how to implement support vector machines. You just call a Convex optimizer. You can do it in 1 day. The weak point there is we assumed this formulation that the reward function is a linear. I can write the reward as a dot product between the weight and some feature that I know that is hard coded. And so, if we have these features, great. If we don't have these features, then we have to do something else. And so if we don't have the features, then we can use generative adversarial imitation learning, our most powerful algorithm. The implementation of generative adversarial imitation learning is hard because it combines 2 hard things, again, an enactor-critic RL method. So I have to deal with this complexity of GAN training. I have to, debug and make sure the learning rates are right, make sure that everything converges. And the reward I get at the end is I have an algorithm which is really super universal, and which, we've seen this example with a car where I don't even have to know what the driver is doing, right? I don't have to know whether they are turning the wheel. I just have to know where the car is, and I can imitate that. And I think that is, there's going to be use cases where that kind of flexibility is going to be appreciated. So the practical tip, which I'm going to kind of try to repeat on and on again, is that don't give up. Behavioral cloning often works well with enough data. If you're implementing imitation learning, try behavioral cloning first. Worst case is you just use it to initialize your policy. And I know that this is the kind of tip that you don't often see in tutorials given by academics, but in companies, so we are very interested in doing research, but we're also very interested in getting something which works quickly. And in cases where you just want something to work quickly, just do behavioral cloning. Okay, cool. So I still have 3 minutes left in that part of the tutorial. So let me give you an overview of the other problems that we can solve in imitation learning. So this is just a taster. I'm not claiming that this list is exhaustive. I just wanted to give you an indication of what's happening. So first thing, we saw this example in behavioral cloning. If only I could ask the expert about what to do in that state, that would help me improve my policy. So actually, you don't have to do it with your eyeballs. You can automate that process. And there's lots of literature about how to do that. And there's algorithms that tell you, now I'm going to ask the expert for that data, and that's going to improve my imitation learning policy by that much. So I can ask the expert for more data. We can, another branch of imitation learning is sometimes we're learning from the expert that has a constraint. So let's say, I'm learning to play tennis, but the expert has a shaky hand, right? So they kind of do the right thing, but their hand is shaking, and that has an impact on their performance. And then there are imitation learning methods that allow me to filter out the noise. So I'm doing what the expert is doing, but without the noise, and then I can do better than the expert in these cases. Another important problem is, can we do imitation learning with partial observability, where maybe I don't observe the whole situation in the game. I just have a small window that I see the world through. And that's a very huge area, so I'm not going to begin to formalize it. But I just wanted to say that, yes, it is possible, and it has been done with very good effect. We can also think about imitation learning, where we have not one agent, but we have several agents, and these agents are communicating to solve a common goal. And there is a team that's demonstrating that, and there's a team that I'm trying to train to imitate the behavior. And that can be done as well. And finally, there's this setting of robust imitation learning where, we can still do imitation learning where at test time, when I deploy this imitation learning policy, which I'm computing, I'm getting a slightly different MDP. So it has to be related, because if it's not related, I cannot learn anything, but it's slightly different. And that allows me to be more robust. So here, an example in practice would be, maybe I'm teaching a robot to do something, and that robot has, become slightly miscalibrated. There's some wiggle in how the robotic joints move. Okay, so this is just a taster. This is not intended to be, I'm not going to talk about the details of these things, but just to give you an indication of what's happening in the field. If you want to read more about imitation learning, I want to recommend 3 modern classics on imitation learning. First paper, Efficient Reductions for Imitations Learning. It's a paper that discusses the shortcomings of behavioral cloning. It is really, behavioral cloning. You should use behavioral cloning in many cases, and if you do, then this is a paper to read. And so I guess I just cannot, recommend it highly enough. Second paper, Apprenticeship Learning via Inverse Reinforcement Learning, which introduces this idea of matching features in the context of imitation learning that we have seen. And finally, the most modern method, Generative Adversarial Imitation Learning, the idea of using GANs to do imitation learning. And of course, there is many more. The reason I'm giving you a reading list of 3 papers rather than 50 is that this is intended as a tutorial. This is not a survey. So I'm trying to give you pointers to papers which, if you know the main concepts in these papers, you have a very good starting point to begin working in this field. It is not my goal to be comprehensive. But after reading these 3 things, you can do your own research and you can follow the pointers, and then you can get a more full picture. So in practice, when you implement imitation learning, my recommendation is this. Start with a small problem. Whenever you do imitation learning, pick a task with a short, wherever you do any kind of RL actually that you want to deploy in practice, start with a small toy problem. Pick a task which has a short horizon, typically less than 10. Get your expert data by training an RL algorithm. You can also demonstrate, but typically on a very small problem, RL works immediately. So you can just get the data really quickly, implement behavioral cloning, and see how behavioral cloning performance changes as you vary the amount of expert data. Because what we really do in machine learning is we process data. And so the behavior of the algorithm, this relationship of how it changes depending on how much data we have, you should have a very good indication of how that relationship looks like for your problem. And very often you will find that you actually have enough data to make behavioral cloning work. Next step, implement apprenticeship learning with features learned by behavioral cloning. And if that is not enough for your problem, you can implement generative adversarial learning. That final step will take you a while. My recommendation for doing it in practice is, first, just make sure that you can compute the divergence between 2 probability distributions without minimizing it. And then second, only when you know that's working, hook it to an RL algorithm that you know works and try to combine. Okay, before we finish, this is just a final slide about Microsoft. So we have this project PIDA that I'm part of at Microsoft. Our goal is to make computer games even more fun. I wanted to take this opportunity to thank all my colleagues at Microsoft Research. If you want to look at information about how we apply reinforcement learning and imitation learning at Microsoft, please have a look at the link that I have provided in these slides. We're slightly over time. I think it would be a good time to take questions. All right. I'm very much looking forward.
Great. Thank you very much, Kamil. So we have actually quite some questions. So I will start with the first one. And so in reinforcement learning algorithms, we often overfit established benchmarks through the use of extensive heuristics, and we cannot generalize for real-life tasks. What do you think can be done about it?
We need more benchmarks in reinforcement learning, and we need more benchmarks for imitation learning specifically. So there has been a lot of work recently about making RL and imitation learning more robust, where the task I'm getting at test time becomes becomes more different than usual than the task I'm getting at train time. So I guess my answer to that is yes. For many kinds of research, we need more benchmarks, and I think that particularly the there are many cases where it is difficult to guarantee generalization in reinforcement learning algorithms, but it does not mean that we shouldn't try, right? So for instance, if we talk about robotic benchmarks, there has been lots of work where we can try to generalize a bit. So I'm getting a slightly different robot at test time. Maybe one of the arms is slightly elongated or a similar concept. Unfortunately, the current situation in the field is that we cannot really so there's no people have done that, and people kind of realize there's an issue, and I agree, but there is not a standard set of benchmarks. So most imitation learning papers that are written are still benchmarked on things like Atari, the standard Mujoko tasks, and these are great, and they show many useful properties of algorithms. But of course, ideally, we would want to use benchmarks which have more, which have a which require more generalization. So that's kind of one point. The second point that I wanted to make is that very often people claim that RL is cheating because we are testing on a training set. And I just wanted to say that I disagree with that. The optimization problem that RL is solving is give me the policy that maximizes the return. And if I can, hopefully in a, using the as few samples as possible. And if I can do that, I've solved the problem. And so if you think of a problem like chess, then it's like saying, so you trained a computer program to play chess really well, and now this argument that if you trained on chess and you test on chess, you're cheating because you're training on testing on the same thing doesn't really make sense, because the whole point was to solve chess, right? So the in practice, the testing regime is going to very much depend on the type of scenario that you're addressing. And if the goal is something like a board game or something like Minecraft, then it totally makes sense to use this setup where we test on exactly the same MDP. If the goal is we actually are going to use it in a setup where the world is different, but we can model that either as a distribution of test MDPs or as a maybe there's one MDP which just has a very large state space. So that's kind of another way to do it. But in any case, I agree, yes, that in many cases, generalization is a very interesting research area, and I hope that it's going to improve. That the ability of reinforcement learning algorithms to generalize is going to improve. So thanks a lot for that question. I think that's a very good point.
And now you just showed a project that you're doing at Microsoft. Are there any other industrial applications for imitation learning that you're aware of?
So I'm definitely aware that the self-driving car industry is very much using imitation learning, and that's why they're collecting so much data of cars, driving various places. But I'm not part of that industry, so I cannot provide the specifics of how that is done.
And what if experts take inconsistent actions in different runs of the same game? How does this affect imitation learning?
So imitation learning requires me to make, so when I specify my objective, if I think about, so let me start with GAIL. So with GAIL, my objective is to mimic the expert behavior, and that's what I declare my goal to be. So if I get data which is noisy, where the expert does something which doesn't really make sense, then I'm just going to create an imitation learning that makes the same mistakes. So it's like, I have a demonstration which isn't perfect, I get a behavior which isn't perfect. If I want a better behavior, I have to improve the demonstration. And there's tasks where this formulation makes sense. There's other tasks where I can do more. So I didn't describe it in detail, but I mentioned this example of the expert playing tennis with a shaky hand, where occasionally the expert just, unintentionally executes actions which are not optimal. And in that case, if I make an assumption about the expert, then I can do better than the expert. And the assumption may involve, filtering the noise out.
And some participants asked about about working with BC, with the BC problem, but they're wondering where can they get expert data and what is the minimal number of data for it to work?
So it's very problem dependent, and it depends on the general question here is what's the sample complexity of reinforcement learning, and we have good results about that for bandits. For MDPs, we have theoretical results which talk about tabular MDPs. It's kind of difficult, so we don't really have a very complete theory of how many samples we need to do reinforcement learning in settings with huge observation spaces, action spaces. However, in practice, I can say for most tasks, one trajectory is often enough. So if your task is to solve, is to just, let's say, play the game for 10 minutes, and you have a recording of someone playing it for 10 minutes, I would expect you to be able to solve that task.
And traditionally, it is difficult to train GANs. So when we apply GANs to imitation learning, how can we avoid the common problems that we face during training GANs to get efficient imitation learning?
Using the same techniques that people in the GAN community use. So there's no silver bullet. Imitation learning is combining a GAN with additional level of complexity. So all the problems that GANs have, we're still gonna have, right? They're not going away. But we can use the techniques that people in the GAN literature have come up with. And I think that a really successful technique is this use of Wasserstein divergences and the idea of enforcing the Lipschitz process. So if I treat the discriminator as a function, the way I train a Wasserstein GAN is I have to make sure this function is Lipschitz. And I can do it in various ways, like the gradient penalty, for example. And in practice, that type of optimization has been tractable and led to good performance. But I just wanted to stress this is not an issue specific to imitation learning. That's just a general GAN issue.
And are you familiar of approaches to hierarchical modeling of a reinforcement learning agent? So are there similar approaches without doing reinforcement learning, or can we imitate a hierarchical agent?
So you could definitely do an imitation learning algorithm which uses a hierarchical policy class, right? So the way we formulated that is I didn't say anything about what the policy class is. You can do a policy class which is a network with many layers. You can do a policy class which includes some hierarchical abstraction, and you can just optimize in that class. And so that's definitely possible, and you don't have to modify the imitation learning algorithms to do that. You could try to tailor-made an imitation learning algorithm specifically for a setting where good hierarchies exist. It is an important research direction. I agree with that.
And are you aware of any modifications of GAIL that also use possibly sparse true environments reward and are not capped by the expert's performance?
So I don't. Okay, so the specifically, so the standard setting of GAIL does not use the expert reward at all, and it's kind of the idea of imitation learning is we don't have access to the expert reward. There have been attempts to combine imitation learning with standard reinforcement learning, where we get some rewards, but it's very much an open it's a very much an open research area, so I cannot give examples right now.
Sample complexity and inefficiency are known problems in reinforcement learning. Do you feel there is any solution to this problem, or where can be a good place to start?
Okay, so I guess so. If you want to study this problem formally, then the way to study sample complexity is to start with bandits, because bandits have very good results, and we have bounds that tell us exactly if I want a policy that achieves a certain performance, this is how many samples we need. We also have results for tabular MDPs. We do not have formal results for deep reinforcement learning for sample complexity. And in practice, I would say if the goal is to do something that works quickly, then increasing sample complexity in deep reinforcement learning is mostly a matter of trial and error. You cannot really have so in the immediate months, I don't think you can have a bound that talks about, if I get these samples, then I'm going to achieve that performance in the general case. However, I wanted to stress one point about imitation learning specifically. In imitation learning, we have this freedom to provide the data that we want to provide, and if we choose that data wisely, if we provide exactly the data that's the most useful, then the amount of expert data that we have to provide in practical cases is often actually quite small.
And what are the most promising directions for research in imitation learning and reinforcement learning at the moment?
Right. So I would say, so I gave kind of a list of these bullet points, and many of these bullet points are problems which still, the solutions can be improved on. I guess the two things that I think are most promising would be robust imitation learning and representations for imitation learning. But this is a subjective take, and I'm not like, there's certainly people who would probably who have slightly different priorities, and these are great as well.
And there are some researchers that consider reinforcement learning to be causal. Do you have any thoughts of this?
Sorry, I just didn't understand the last word acoustically. Is reinforcement learning with what?
To be causal, causality is connected to causality.
All right. Yes. So there is the so this is right. So this is another interesting idea. So the idea of using causal formalisms to improve imitation learning agents, it is definitely very promising. I guess the kind of classic work in that space that is very well known is the principle of causal entropy, which is it's a type of inverse imitation learning that I haven't discussed in the tutorial, but it's quite popular. There is also attempts to apply causal reasoning to which features I need to train an imitation learning agent, and it's a very growing. It's a rapidly expanding research area. So yes, I agree, it's promising, but at this point, I don't think I can say more about it.
And to conclude, maybe you can tell us a few words of how did you get started into reinforcement learning? What led you to this field?
So the reason I originally started doing reinforcement learning is because it's this very generic framework for making a controller for anything. So I didn't start with imitation learning. I started with vanilla RL, and the idea is, given just any situation, I can synthesize a controller just from interactions. It's very appealing and a very useful thing if we can do it well. And then more specifically about my Microsoft job, I'm really excited about making computer games more fun to play. And I think, that is just part of what drives me to develop these algorithms and to improve them. And it is very satisfying to see the, basically, the kind of enjoyment that we can generate with what we do.
Well, thank you very much, Kamil. It has been insightful. The participants have learned a different aspect. We have earlier at the school reinforcement learning, but from a different perspective, more the robotics side. So I am sure that this side from imitation learning is also very interesting and exciting for them. I wish you a very nice day.
Thank you, and have a nice day as well, Rodrigo. It was great.